Okay, so sections 6.4 and 6.5 are about infinite series of functions. And as I mentioned in the pre-video notes, that means that we have a lot of results that we kind of get for free from the convergence of sequences of functions. Right, so we define infinite function series as converging when their sequence of partial sums converges. And so all of the results from the sequence convergence material translate almost immediately to results about function series. So those are kind of outlined in the notes. I'm only going to focus on one particular result that is not explicitly in the text, having to do with power series. So this is in section 6.5. And really the work of 6.5, even though it's kind of a long section, but the point of it is so that we can get to a place where we know we can treat power series like we're used to in calculus. So in particular, we can differentiate them term by term and know that the derivative of the power series is the derivative of the function it represents, and that the power series of the derivatives will converge in the same or inside the same interval as the original. So we're going to sort of fill in the main hole in that argument in this presentation. So I wanted to kind of sum up what's happened in the previous results for the section. And that is that if we start with some power series that defines a function f of x, we know that that converges in some interval of convergence. And we're sort of thinking of an interval broadly in that it could be all of R, that would be an infinite interval, or it could be only the point 0. It's kind of a degenerate interval. And then what we normally think of as an interval, some symmetric interval from minus R to R, where it may or may not converge at either or both endpoints. So we always refer to the interval of convergence of a power series, though that's kind of, we have a sort of broad understanding of what that means. So a few of the results we can summarize by noting that if we're strictly inside the interval of convergence, so we are avoiding the endpoints for now, then the power series will converge absolutely there. And if you take a compact set inside that interval, then you get uniform convergence, which is nice because that guarantees that the function it represents is continuous there. Now the endpoints are a little bit tricky, and in the pre-video notes I've kind of omitted the results that take care of what's happening at endpoints. So those are based on Abel's lemma and Abel's theorem. So you can take a look at those if you like, but in this presentation we're just going to avoid the endpoints because I think it's fair to say that most of our interest is inside the interval of convergence anyway. So this is the theorem we're going to prove today. If the power series converges on some interval, then the power series of derivatives converges there as well. Now, one of the things that makes endpoints tricky is that if the original power series actually converges at one or both of the endpoints, that's not enough to tell us what the series of derivatives does at the endpoints. So that throws a little bit of a wrinkle into things. But as I mentioned before, we're just going to ignore what's happening potentially at the endpoints and focus on this doubly open interval minus R to R. So the news of the theorem is that if you have a power series that converges on this interval, its derivative series also converges on that interval. And then we sort of reapply the results from the section where, well, that means that the series actually converges absolutely there, and it converges uniformly on compact sets. which means we have a series of derivatives converging uniformly inside of our interval of convergence. And that's enough to give us that we can differentiate the function the original power series represents term by term. Okay, so this theorem will imply that if we define f of x as a power series, and this converges inside minus r to r, then f prime of x is exactly what we would want it to be. It's the series of derivatives. And that works for every point inside the interval of convergence. And moreover, we can reapply this theorem so that f double prime would be n times n minus 1, a n x to the n minus 2. F triple prime is defined there. All right, so this combination of results basically gives us that power series are infinitely differentiable inside their intervals of convergence. And, right, they work just like you would hope. All right, so let's take a look at the proof of this theorem, or at least kind of a sketch of the proof. All right, so we're going to take some point x that's inside the interval of convergence, and we want to show that our series of derivatives converges there. So we're going to consider this series of derivatives at x. And show convergence. All right, now because x is inside the interval minus r to r, we can fit a number, a real number, between absolute x and capital R. So let's let r be such that little r strictly bigger than absolute x, but smaller than the endpoint capital R. Then if we think about the series of absolute values of the derivative, I can rewrite that as follows. So I'm going to have absolute an x to the n over, let's see, r to the n. So those should be minus ones. And then n r to the n minus 1. I actually don't need an absolute value around the r. I know it's positive. So let's double check that we haven't changed anything. We basically just, one of our favorite tricks, multiply by a clever form of 1, r to the n minus 1 over r to the n minus 1. All right, now the reason that this is useful, let me do one more step here. So this is a to the n, and now I'm going to write this as over r times r to the n times x over r to the n minus 1 times n. All right, so again, multiply top and bottom by r, so that r to the n minus 1 is now just an r to the n divided by r. And then I just brought the exponent outside the parentheses, and I know I'm multiplying still by n. So the point of all of this algebra is that because absolute x is less than r, I have a ratio here that's less than 1. And so as I raise that to higher and higher powers, I'm going to drive it to 0. And the presence of the n actually is not enough to overcome that. Right? So you can maybe think of this as an exercise, but n times a ratio raised to the n minus 1 is going to go to 0. But what's important about that is that this expression is bounded by some capital M. So this is less than or equal to some capital M for all n. Right? So it's a sequence that goes to 0. And in fact, we can show that it's a decreasing sequence to 0, and so it has a bound. So that means that my series is less than or equal to m over r, which is just a constant, times the sum of a n r to the n in absolute value. And this is where we're basically done, because we make use of the fact that since little r is in the interval minus r to r, note this is the original power series. And so we know this converges absolutely by previous work. So it converges by assumption because we're inside the interval of convergence, and then since we're inside the interval of convergence, that convergence is also known to be absolute. And that means by comparison, our original series also converges absolutely, and because it converges absolutely, it converges at the point x. So that basically completes the proof that a series of derivatives converges in the same interval as the original power series. So this all implies that n, a n, x to the n minus 1 converges, and that's the end of the proof. All right, so once we have that, then the previous results guarantee that the series of derivatives also converges uniformly on any compact set inside the interval of convergence. And so we get this, which is kind of the point of the whole section, that if we start with a power series that defines a function, you can differentiate that function by taking term by term derivatives, and then you can repeat that process as often as you like.